Alright, so this is our AP Chemistry Chapter 20 lesson view. This is Part 3, and I'm going to cram in Section 20.5 and 20.6. I'm going to try not to let this video be too long, so I'm going to try to get through it because it's a lot of math. I'm going to try to get through the math as quickly as possible because I really don't want to have to split this up into two. So let's go ahead and get started. Alright, so we're still talking about free energy, we're still talking about E cell or your EMF for electromotive force. And so as we talked about before, it's the E of reduction minus the E of oxidation. So let me put that back up on the board just so you can refer to that throughout the video. Alright, so our E of our cell is our E of reduction minus E of oxidation. So a positive value of E indicates a spontaneous or thermodynamically favorable process, and a negative value of E indicates a non-spontaneous or thermodynamically unfavorable process. Okay, so remember, when it comes to favorability, you want negative delta G, negative delta H, positive delta S, positive E cell. Alright, so that's what we're looking for. So it says, using standard reduction potentials in Table 20.1, determine whether the following reactions are spontaneous under standard conditions. Okay, so don't worry, I'm going to give you the numbers out of Table 20.1, but first of all, let's go ahead and figure out what's oxidized and what's reduced. So remember, an element by itself is 0. This would be positive 1. This would be positive 2. This would be 0. So I'll pull out, for example, copper.
Caitlin Boyd,
Oh my gosh.
Laura
Are
Light,
we
you
going to
needed
do
an
this all
officer
day?
checkout, please.
We
Caitlin
obviously
Boyd
are.
and
So
Laura
I
Light,
apologize.
you
I
needed
don't
an
have
officer
time to do
checkout.
this video any other time. Alright, so since it went from 0 to positive 2, that's oxidized. And since hydrogen went from positive 1 to 0, that was reduced. Okay, and see y'all, the important thing is you know oxidation and reduction have to happen together. So once you figure out that one of them is oxidized or reduced, the other one just has to be the opposite. So on the AP exam, save yourself time. Once you figure out one of them, the other has to be the opposite, and you don't necessarily need to spend time doing oxidation numbers for that one. Okay, so I know my E cell is my E of reduction, so then I would find the hydrogen number, which in this case is, whoops, where am I? I'm on the wrong page. I'm trying to go ahead and get ahead, which is 0 volts, minus the copper number. And the number for copper will be 0.34 volts, just like that. So once I subtract, I get negative 0.34 volts. So it says, determine whether the following reactions are spontaneous under standard conditions. Since, of course, it's negative, this would be non-spontaneous or thermodynamically unfavorable. Alright, and so that's all you have to do. Just figure out what's oxidized, what's reduced, do your formula, and then if it's a negative number, it's not spontaneous or thermodynamically favorable. If it's a positive number, it is. Alright, so let's look at this one. So Cl went from 0 to negative 1. I went from negative 1 to 0. So Cl was reduced. There was a gain in electrons. And I was oxidized. There was a loss of electrons. So then we just plug into our E cell. So my reduction, I would look up the number for the chlorine reaction, that half reaction. And so that is 1.36 volts. And then I would just subtract the number for the iodine's reaction, which is 0.54 volts. And so I end up getting a positive 0.82 volts. So this one would be spontaneous or would be thermodynamically favorable. So my marker's not super fantastic, so I'm going to go ahead and trade out right now. Last thing I want is to take longer over having a marker that's not great. Alright, and so remember on the AP exam, even on the textbooks, we still use terms like spontaneous and non-spontaneous. On the AP exam, they're going to focus on thermodynamically favored and thermodynamically unfavored. Alright, so y'all try these. Before you try them though, I need to give you the numbers. Okay, so let's see, for the iodine reaction and the copper reaction, for the copper reaction, it's 0.34 volts. For the iodine reaction, it is 1.195 volts. All right, for next, we have the mercury and the iodine. Okay, so for the mercury reaction, it is 0.854 volts. And for this iodine reaction, it's 0.536 volts. And then for the bottom one, you have the sulfurous acid and the manganese. So the sulfurous acid is 0.45 volts and the manganese is negative 1.18 volts. Alright, so now pause it, try it. I'll assume you've done those, and so let's look. We're trying to figure out what's spontaneous and what's not. All right, so I can see, so like for a long one like this, you would not want to sit there and figure out all the oxidation states. Okay, so I can see, all right, iodine is going to have the water, you're going to have your iodate, your hydrogen. That one's kind of in depth. Okay, but I can see that the copper is really easy for me to tell. It went from +2 to 0. So that means copper was reduced, so that means my iodine is oxidized. And see, then I don't have to come up with all the oxidation numbers for it. Okay, so then I just do my E cell is the reduction, which is the 0.34 volts, minus the 1.195 volts. And so you should have gotten negative 0.855 volts, and so that would be non-spontaneous or thermodynamically unfavorable. All right, so then I look at my bottom one. So I'm just going to pick mercury. It went from +2 to 0. So since it went from +2 to 0, it was reduced. That means iodine was oxidized. Okay, so again, save yourself some time of having to do all these oxidation numbers. All right, so the reduction is mercury, which is 0.854 volts, minus the iodine, which is 0.536 volts. So once I subtract, I ended up getting 0.318 volts, and so since it's a positive number, it is spontaneous or thermodynamically favored. All right, and so then our bottom one. Again, I don't want to deal with all of this and the water, so I'm just going to look at manganese. Okay, remember, the test is timed. You have a specific amount of time, so you have to focus on that. So manganese went from 0 to +2, so it was oxidized. That means my other was reduced. So then I just plug into my E cell. So I plug in my reduction, which is 0.45 volts, minus my oxygen, which is a negative 1.18 volts. And so notice when you subtract a negative, it becomes positive. And so I got 1.63 volts. And so again, since it's positive, it is spontaneous. All right, so hopefully these aren't too bad. I don't have time to talk about how I hope it's not too bad and recap what you got to do because we got to move on. The Nernst equation, which we're going to end with in the last section, takes up a good amount of time. I don't want this video to be too long. I'm dreading making the rest of this. All right, so next we're going to learn a formula that connects the E cell to Gibbs free energy. Okay, and so this is on your formula sheet on the AP exam, but I'm just going to put it over here so that way we can refer to it without coming back here over and over and over again. All right, and so delta G, of course, is Gibbs free energy. We've already talked about that. N is number of moles, like usual, but it's number of moles of electrons. Okay, and then F is something new we haven't talked about. Is Faraday's constant. That is also on the formula sheet.
Teachers and students, please pardon this interruption.
Oh my gosh.
Rain Thompson and Laura Light, you're needed for checkout, please.
It's
Rain
Friday before
Thompson
spring
and Laura
break,
Light,
just letting you
you're
know.
needed for checkout.
So, and it's 4th period at our school, which is the last period of the day. So obviously everyone else is starting spring break early. All right, so Faraday's constant is just this. This is on your formula sheet. And then E, of course, is your cell potential, your EMF, your E cell, whatever. And so because of the formula, because of this negative sign right here, if E is a positive number, which is favored, then delta G will be negative. And so you have a thermodynamically favored reaction. All right, I'm really struggling to get through this video in a good mood because of these announcements. All right, it's okay, I'll make a good mood for y'all. All right, so we're going to use the potentials that we find in table 20.1. We're calculating the delta G and we're calculating K. Okay, so we're going to calculate our K also. All right, so let's do our delta G first. So before I do delta G, I need N and I need E. I know I have F because it's a constant. All right, so I look at my reaction. I don't see electrons in the reaction. So what you do is you pull out one of the half reactions. Okay, see, I always like to pull out the simplest part. Like, I don't want all of this when I can just pull out silver and silver ion. So I pull out my half reaction just like this. And then remember, when you balance half reactions, it's not just about the atoms, it's about the charge. So I can see this side has a 0 charge, this side has a +4 because there's 4 silvers that are positive. All right, so that means on this side I need 4 electrons to balance out that charge. So that's how I know my number of moles this time is going to be 4. All right, and so then I need to do my E cell. So this is where I would pull those numbers from that table 20.1. So for silver, we are going from 0 to positive 1. So silver is going to be oxidized, and so my other is going to be reduced. Okay, so I would look up my numbers, and then I would do my E cell. So it's the reduction, which of course is the oxygen. And so that number, like I said, it comes from the chart. That number is, whoops, where is that number? Oh, there it is, okay. I'm looking at a whole lot of math here. All right, 1.23, and then I subtract my oxidation, which is the silver. The number for silver is 0.799 volts. So when I subtract, I get 0.431 volts. All right, so now I have my N. I always have F. I have my E, so I can calculate delta G. So delta G is just negative NFE. So then I just plug in. So the amount of electrons is 4 moles. Faraday's constant is 96,485 joules per mole volts. Okay, so joules on top, volts and moles on bottom. And then I just multiply by my E cell, which is 0.413 volts. So my moles cancel, my volts cancel. And so for delta G, I ended up getting negative 165,954.2 joules per mole. Just like that. Okay, you can calculate kilojoules per mole instead if you'd like by moving your decimal over 3 spots. In that case, I got negative 165.95 kilojoules per mole. Either of those would be fine because, of course, it didn't specify. Like it just said calculate delta G. It didn't tell me if it had to be in joules or kilojoules. Okay, but the problem is it also wants K. Okay, so we have our formula where we've rearranged it. Remember how we use K as E to the delta G over RT, but it's negative. Y'all remember that formula? Hopefully you do from one of the previous videos. Okay, it started out as delta G equals negative RT ln K. Like this is just me rearranging this and solving for K. That's how you rearrange this formula. So then we just plug in. So E to the negative, I plug in my delta G. And so in this case, because of the R value being in joules, I plugged in joules for this. If you want to plug in kilojoules, you'll have to change that R value because remember it's joules per mole Kelvin. All right, so I kept my joules for this. So I plugged in negative 165,954.2 joules. And then I divide by my R, which is 8.31 joules per mole Kelvin. And then I multiply by my temperature, which my temperature is 298 Kelvin. So just to clean this up a little bit, okay, and then my joules, my mole, and my Kelvin all cancel, which is fine. K has no units anyway. This whole number right here ends up being about E to the 67.015. Okay, and so then once I solved, I got 1.27 times 10 to the 29. Now I'll go ahead and tell you, if you want to talk about rounding errors, when you do e to a power, you get a lot of rounding errors. There's a big difference with just small changes. And so what I want you to notice is I did not hold strong with significant figures throughout this. Okay, so my number is going to be somewhat off because I didn't count significant figures throughout. What I did was I just cut off 3 at the end. Okay, so that's not preferable, but that's just what I did in this one because I wasn't counting significant figures. So if you are off by some decimals here or you round to a different place than I did up here, then you're going to get kind of a significant difference in your answer. Okay, but the important thing is, to make sure you can do the problem. We all know how to do significant figures. We learned that back in Honors Chem, so we can just do those from now on. All right, so then it says, now this time I'm going to cut this one short, okay, because I don't want to redo this whole thing. All right, so then it says, what are the values of E, delta G, and K when the reaction is written this way? Okay, so y'all, I'm not going to recalculate them. We're just going to talk about would they go up, go down, remain the same. Okay, because again, I got to save some time because the last section is so long. All right, so let's look at what's happened with the reaction. What we did was we took this reaction and we divided it by 2. So see, look at my coefficients, 4, 1, 4, 4, 2. So now it's 2, half, 2, 2, 1. Okay, so what would happen to E? So once we say we half it, a lot of you want to say E cuts in half. But remember, E will change sign if we flip a reaction, but if you multiply or divide a reaction by a number, E remains the same. So it's going to stay the same. Okay, now let's talk about delta G. Okay, and remember that was a negative number. So now, if I pull out that same half reaction, like I did before, I have 0, but now I only have positive 2. So I only need to add 2 electrons to this side. So that's going to change my N. Remember, my E remains the same, F remains the same, N is going to change. So N is now a smaller number, so G is going to be less negative. Okay, that's what's going to happen to G. It's going to be a smaller number, but it's going to remain negative. Okay, and so then, because delta G is negative, that's going to make my power for E when I'm solving for K lower. So K will be less positive, let's say. Really, it means you end up with a smaller exponent. Okay, so I'll just let you know like what actually happens because I have the math on here. So for this one, let's see, E remains the same. Delta G actually changes to about negative 83 kilojoules per mole instead of negative 165. So see, it's less negative, just like we predicted. And then K was 10 to the 29, but now it's only 10 to the 14. So it's still a positive number. It's still greater than 1. It just has a smaller exponent. All right, but like I said, I didn't want to have to redo all that math just for time's sake in this video. All right. I don't want an 80-minute video if possible. All right, so let's look at our next one. So it says, for this reaction, what's the value? Oh, y'all try this one. But hang on, I got to give you some numbers real quick. Okay, so you'll need the number for the nickel reaction and the chromium reaction. Okay, so for the nickel reaction, your number is negative 0.28. And for your chromium reaction, it's negative 0.13. Okay, so y'all try this one. I'll assume you paused and tried it. Let's look at it together because I don't want to do this all class period. All right, so the easiest way to tell my value for N is I pull out the easiest half reaction to look at. Okay, so I can see that 3Ni with a positive 2 yields 3Ni. So I need to balance those charges. So here I have 0. Here I have positive 6. So I actually need to add 6 electrons. So what's my value for N? It'll be 6 moles of electrons. Okay, then it says use data in Appendix E to calculate delta G. All right, well we have our N, we always have F, so now I need to do my E cell. All right, so nickel was positive 2. It went to 0, so it was reduced. That means my chromium was oxidized. All right, so I just plug into my E cell. So it's the reduction, which is negative 0.28 volts minus a negative 0.13 volts. And y'all make sure you notice if you are minusing a negative, okay, because you do end up making that positive. But I don't want you to forget that just because you put a subtraction sign, if it's negative, you still also put the negative sign. So for this one, I ended up getting, whoop, I keep losing my spot. All right, there we go. I got negative 0.15 volts. Okay, so that is not favorable, which means that my delta G, once I plug into my formula, should be positive. All right, which is exactly what happens. So we have negative NFE. So then I plug in. So negative 6 moles times my Faraday's constant, 96,485 joules per volts and moles, times my E, which is negative 0.15 volts. So my volts and my moles cancel, and so I ended up with 86,836.5 joules per mole. And of course, you are more than, and see, it's a positive number, which is unfavorable. So you could have changed that to kilojoules per mole if you wanted to, but either way, you would not technically want to keep all those significant figures. However, I did when I went ahead and finished this off. All right, so we calculate K. So remember, K, I'm just going to do a rearranged formula again, is E to the negative delta G over RT. And so then I just plug in. So I have a negative 86,836.5 joules per mole I'm going to plug in that R value, 8.31. Remember, if you decided to change it to kilojoules, you got to change your R value in kilojoules too. Per mole Kelvin, and then what temperature? 298 Kelvin. So again, I'm going to clean this up some. And remember, I went out way too many significant figures, just letting you know that. Sometimes I get tired of counting significant figures. I know y'all do too, and sometimes teachers will do also. Alright, so I get e to the negative 35.07. So remember, if you rounded anywhere differently than I did, you're going to get a different number here, and it's probably going to make a large difference in your answer. Okay, so I end up with 5.88 times 10 to the negative 16. And so that's why significant figures are so important, which makes sense because this is not a favorable process, so K is super small because, of course, that favors reactants. Because remember, if one direction's unfavorable, the opposite direction's favorable. All right, so hopefully you got that one right. Whew, I feel like this video has already been so long. I kind of want to split it in half even right now, but I just want to go ahead and finish. It's the last one. All right, oh, okay, well, you know what, I'm going to power through. I saw section 6, so I'm going to power through. All right, so now we're going to talk about when we're not at standard conditions. Okay, because remember the little degree sign where we say not, like E not, or E cell not, it's implying standard conditions. And so for aqueous solutions, that's like 1 molar, or otherwise it's the standard state of an element. So there's something called the Nernst equation, and that's what we use if we're at non-standard conditions, because of course then we can throw a Q in there. So this allows us to solve for E using non-standard conditions for Q. Now, the formula on the AP exam formula sheet looks slightly different than this. Like they have R and T in it, and they have a natural log where you would need to do E instead of a log. And so this is the same formula, it's just they condensed all the rest of that and gave us this constant right here. Okay, so you can use either formula, but it's to my understanding you shouldn't be plugging into the formula on the AP exam. You just need to conceptually understand it. That's just my understanding. I could be totally wrong, which is why I'm covering it anyway. All right, so let's move on. So we're on sample exercise 20.11. So it says calculate the EMF, which is just your E cell, at 298 Kelvin generated by the cell described in sample exercise 20.4 when we have these concentrations right here. Okay, so y'all, first of all, let me just give you a friendly reminder of what the cell described in 20.4 was. So here was our reaction. Okay, so we did this one already, but let's just look at our reaction again. Alright, oh, and I put my states of matter, so I guess it told us the states of matter here. Alright, so that was my reaction. Okay, so if we were at standard states, any of those aqueous things should have been 1 molar. Okay, but of course we can see that not everything was. Alright, so we're going to plug into our formula. I'm actually just going to pull our original E value from the previous question. Okay, so we already calculated the E cell for this. That was one of the questions. We calculated it as 0.794. Okay, because we don't need to waste our time doing that again. All right, and so then I can look at my reaction and I can pull out a half reaction. So this seems like the easiest half reaction to pull out. So I have 6I negative yields 3I2. So this is a negative 6, this side is 0, so I need 6 moles of electrons. So there's my N, okay? Because the whole thing is I'm trying to plug into this formula right here, okay? And so I need my N value for that. So see, now I have my E naught already from our previous problem. I just figured out what my N is, and so now I can plug in my Q. Okay, and y'all, you know how to do Q. Okay, it works just like K. It's the products over the reactants. Okay, so let's plug into this thing. So my E overall is my E naught, my 0.794 volts. All right, and then it's minus, and then it gives me that constant, the 0.0592 volts over N, which my N is 6 moles of electrons, like we just decided it's right here, 6 moles of electrons. All right, and then times log of Q. Okay, so remember my Q, we don't include solids or liquids. Okay, so my Q is going to be my chromium over my other three, my chromate or dichromate, hydrogen ion, and iodine ion. But don't forget to raise them to the powers of the coefficients. So it's going to be the chromium. So I find my chromium. So it's 1.0 times 10 to the negative 5. But I'm going to square it. All right, and then over my dichromate, which is 2. I'm not going to do anything because that's a coefficient of 1, times my hydrogen, which it told me is 1. But I'm going to do it to the power of 14, but it doesn't really matter because 1 to the power of anything is just 1. And then I do my iodine, which in this case is 1. I'm going to do it to the power of 6, which again doesn't really matter. So once I solve this whole long thing, I end up getting 0.896 volts. Okay, so y'all, the important thing is to realize that the voltage has increased. Okay, so y'all, if you look, what have we done? We took this from 1 molar to 2 molar, so I increased this. These both stayed 1 molar, and then I decreased my chromium from 1 molar. And so anytime you add more reactants or take away products, your E cell will increase. Or if you do the opposite, like if I take away reactants or add products, your E cell will decrease. Okay? So it's a conceptual problems as to my understanding what will be on the AP exam more than plugging into this formula. But just in case it's on there ever, I'm going to plug into it. All right, so this one, I'm going to give you some information before you try it. So this one is based on sample exercise 20.6. So let me give you some information for that real quick. So this was our reaction. And again, because we've already calculated the E cell of this, I would not recalculate, like the standard of it. And so our E naught for the cell is 2.2 volts. Okay, that way you don't have to recalculate that. Okay, so y'all try this one. I'll assume you paused it and tried it, and let's look at it together. All right, so first I need to figure out my N, okay, because I have my E naught, I have my E under standard conditions, so I need my N. All right, so I'm going to pull out my aluminum. So I have 2 aluminum solid yields 2 aluminum with a positive 3. So this side's 0, this side's positive 6, so I need 6 electrons. So now I got my N. So then I'm ready to plug in. All right, so see how easy it is, like once you know what you're doing? So my E, my non-standard E, equals the E naught, which in this case is 2.2, minus, and then I have that constant, the 0.0592 volts over 6 moles of electrons. Okay, I got that from here, times the log of Q. All right, so I just have my aluminum and my iodine, and nothing else, like nothing on like products over reactants. So there's nothing on bottom this time because both of my reactants are solids. All right, so I just do my aluminum, which is 4 times 10 to the negative 3, but I'm going to square that, and my iodine, which is 0.01, but I'm going to raise that to the 6th power, just like that. Okay, so we actually don't even have anything on the bottom for Q, and so I end up getting 2.37 volts. Okay, so again, what I want you to notice is it increased, so let's look at why. All right, so I took my aluminum ion and I decreased it. I took my iodine and also decreased it because they're not 1 molar. And so remember, if you take away products, then or add reactants, your E is going to go up, which is exactly what happened. All right, so let's keep going. All right, I've got to at least beat announcements. Announcements, come on, my video's over. All right, oh my gosh. Okay, so if the voltage of a zinc hydrogen cell, like that in figure 20.11, so that's just a figure in the textbook, is 4.5 volts at 25 degrees Celsius when zinc is 1 molar and the partial pressure of hydrogen is 1 atmosphere, what is the concentration of H+? So in this case, we can use our formula to solve for one of the concentrations. Okay, so let's get started. So it tells me on my thing that this is what was important from this figure 20.11, so that way if you don't have your book, you can see it. So it gives me the reaction. It also tells me, it gives me the E cell, the knot under standard conditions of 0.76 volts. And it also tells me, it gives me the number of electrons. Okay, so apparently I can get all of that from looking at the actual picture in the book. And like I said, it's just figure 20.11. All right, so that's what I pulled from the book. And so then, let's see, it tells me that this is my E. Okay, so not only do I have E naught from the picture, it's told me what E is. Sorry, that was a weird looking E. It told me what E is, and then it told me what my values are for the zinc and the hydrogen. Okay, and so, oh, sorry, the zinc and the hydrogen gas. What I'm looking for is the hydrogen ion concentration. And of course, zinc's not going to be in there because it's a solid. So then I just use my formula. Okay, so we know that E is E naught minus 0.0592 volts over N times log of Q, which I just went ahead and plugged in what Q was, so it's going to be the concentration of zinc times the partial pressure of hydrogen. That's kind of weird that they gave you concentrations and partial pressures, but it doesn't matter. Remember, Q and K have no units. All right, over my concentration of H plus, but it's going to be squared. Okay, so in other words, I've got to take this whole thing and solve for H plus. All right, so what I started doing was I started plugging everything in. So I know my E is 0.45 volts. I know my E naught is 0.76 volts. Obviously, a constant doesn't change, so minus the 0.592 volts over my N, which the picture told me is 2, and then log of, and then my zinc is, it told me 1 molar. My hydrogen is 1 atm over, I'm just going to plug in an x for that, so that ends up being x squared. Alright, and so then y'all, all I ended up doing was solving for x. I probably didn't show all the steps, but I'll at least write down what steps I did. Okay, so the first thing I did was I subtracted this to the other side. So I got negative 0.31 volts is negative 0.0296. So I went ahead and divided that. And then I said log 1 over x squared, because of course 1 times 1 is just 1. Alright, then from there, I divided this number to the other side, so then I ended up with 10.47 is a log of 1 over x squared. Okay, so I just divided my number to the other side, and so negative divided by negative is how I got positive again. So then, of course, to do anti-log, you do 10 to the power. So I said, okay, well 1 over x squared is 10 to the 10.47. Okay, and that's how I did anti-log. And so that ends up being 2.95 times 10 to the 10. All right, and then at this point, I just started writing, like I went ahead and flipped both sides or took the inverse of both to get x squared on top. So I got x squared is, like I said, I started skipping steps at this point because this is very long and tedious. And then I square rooted, and so I got x is 5.82 times 10 to the negative 6 molarity. Just like that. Okay, so y'all, again, you got to think, on the AP exam, it's timed. This would take an incredible amount of time to solve on the AP exam. So that's why they're not big on you plugging into the Nernst equation. They just want you to understand that how Q relates to E. Like, how does E change when you change the reactants and products? Okay, so y'all try this one. I'll assume we need to know stuff again. Okay, same figure. Okay, same figure, but different E this time. Okay, same figure, and then this time you're trying to calculate pH. So once you get H plus, you'll need to do pH. So if you need to, don't pause the video just yet. And oh, I gotta put the information you'll need back up here. But if you got it from last time, then you can just use it from last time. All right, so let me put that information back up. This is where not having the textbooks is really annoying. Alright, now remember, we decided that E naught was 0.76 volts, and we decided that N was 2 moles of electrons. All right, so y'all try this one. I'll assume you've done that. And my gosh, let's do it together. All right, so we know that this is my E. All right, we got our E naught. Gosh, what is with me writing E's today? All right, we got our E naught, we got our N, and we have 2 of our amounts. So we're setting it up just like last time. Okay, so I'm going to try to skip a little bit more steps this time on how I solved it, just so like I'm not even going to write the formula, I'm just going to start plugging in just to save some time. All right, so we have our E, which is 0.45 volts. We have our E naught, which is 0.76 volts minus 0.0592 volts over 2 moles of electrons, times log of, and so again, we have just our zinc, which our zinc in this case is, oh, there it is, it was so far away, 0.1. I don't need the molarity because it doesn't matter, Q has no units. All right, and then it's times the H, which is still 1 ATM, and over, we still don't know, x squared for my hydrogen. Don't forget to square it because it has the 2 in front. All right, and so then I started solving. Okay, so I'll give you, I'm not going to give you all the steps. Let's just figure out, I'll just give you all the steps. All right, so I subtracted this to the other side. Whoops, I just grabbed the wrong amounts. All right. Oh, good, I didn't. Okay, I grabbed this wrong amount. I'm sorry, y'all, I was looking at the wrong one. For those of you who have me in class, y'all know if I start rushing, I start making mistakes. So I apologize about that. I was copying the wrong one, but everything else is good. That's convenient. Okay, so sorry, I grabbed the wrong E value. The E naught's the same. This number's the same. The moles of electrons are the same. But thankfully, I wasn't looking at my paper when I grabbed those numbers. All right. So once I started solving, I of course first subtracted this to the other side. So I got negative 0.218 volts. And then that is negative. And then I went ahead and divided this 0.0296 times log of, in this case it's 0.1 over x squared. Okay, so last time it was 1 over x squared, this time it's 0.1. Okay, so I'm going to skip some steps now. Okay, so eventually you're going to get to where x squared over 0.1 equals 4.37 times 10 to the negative 8. So then you would multiply both sides by 0.1. You would get to the point where x squared equals 4.37 times 10 to the negative 9. And then you would square root. And so you would get x equals 6.61 times 10 to the negative 5, and that would be molarity. That would be your H plus. But they didn't ask me for H plus, they asked me for pH. So then I would just do one last step. I know, like, how can it possibly get any longer? It just did. All right, so I would have to do negative log of that, and then my pH ends up being about 4.2. Okay? Whew. So again, now you can see why we don't like plugging into it too much, because especially if you're just solving for one of the amounts, it takes a while. Okay, so y'all, you've got to get used to where you can solve something like this. Okay, like if you were struggling where I skipped steps in showing you how to solve, then you need to come to me for tutoring on that, because, I mean, you got to be able to solve an equation. All right, so last thing we have to talk about, thank goodness, is a concentration cell. That's a cell based solely on the EMF generated because of a difference in the concentration of the 2 half cells. The cell will operate until the concentrations are equal. So here we have a small concentration of nickel ions. So this is low Ni with a 2 positive. Here I have a large concentration. So this is high Ni2 positive. All right, so what's going to happen is we need the concentrations to be equal. All right, so I want, like this one right now is 1 times 10 to the negative 3. This one is 1. So we have a lot more nickel with positive 2 over here. Since there's so much nickel with positive 2, our electrons are going to head in that direction. Because what they're going to do is they're going to grab the nickel positive 2s, and then it's going to deposit on the electrode as nickel solid. And it will do that until the concentrations match each other. So the bigger the difference in the amounts, then of course the longer the battery will run. Oh my gosh, this is a long question. All right, whoops, oh, I already got the answer. Don't look at the answer. Oh, okay, just pretend like the answer's not there, because I didn't animate it, I guess. All right, so a voltaic cell is constructed with 2 hydrogen electrodes. Electrode 1 has pressure of hydrogen at 1 atm and an unknown concentration of H+. Electrode 2 is a standard hydrogen electrode where you have 1 molar H plus and your partial pressure is 1 atm. At 298 Kelvin, the measured cell voltage is 0.211 volts, and the electrical current is observed to flow from electrode 1 through the external circuit to electrode 2. Calculate the H plus for the solution at electrode 1, and what is the pH? Obviously, I already have the pH right here for you, but we're just going to pretend like I don't have that yet. Oh my gosh, this video is getting so long. Alright, it's okay, I'm going to power through. Alright, so we're using our formula. Oh gosh, I hope you can even see over here. Right here. Okay, and so things that you're going to have to pull from the textbook are the E for your half reactions. Okay, so your E for your half reaction for hydrogen is just 0 volts. So since both reactions are the same, your E cell is just 0 volts minus 0 volts. So it's just 0 volts. Okay, and again, you can find that in table 20.1 of your textbook. All right, so next we got to find that N value. Okay, so what we have happening here is this is our half reaction. Okay, so we have this right here yielding this right here. All right, so I have positive 2 on this side and I have 0 right here, so I would need 2 moles of electrons. So in other words, my N is going to be 2 moles of electrons. All right, and then I'm ready to just start plugging in, okay? So again, I'm going to go fast because this video has been so long, announcements are about to come on. All right, so I'm sorry if I'm skipping any kind of important information. I just have to finish the video at this point. All right, so my E, they told me, is the 0.211 volts. My gosh, I don't even have room. My E naught, we just calculated, was 0 minus the 0.592 volts over my N, which is 2 moles of electrons, times log of Q. I don't know how far the video actually goes this direction, so I'm going to have to bring Q down here. And then all steps of solving, I'm going to have to skip that. Okay, so just pretend like my Q is right down here. So here's my log stuff that I'm going to plug in. Okay, so my log ends up being the hydrogen ion concentration squared over the hydrogen gas concentration. Okay, and so we don't know what the hydrogen ion concentration is. Remember, that's what we're looking for. So that's going to be x squared over 1 squared for my atmospheres. All right, so I solved all that, and I'm just going to go for it. Like I just solved this whole thing for x. So x ends up equaling 2.72 times 10 to the negative 4 molar. And so then from there, I have to get pH. So of course I do pH is negative log of this thing times 10 to the negative 4 molar. And so I ended up getting about 3.57. Again, I'm sorry. I know that explanation was horrific, but I don't have any room to write it, and I'm running out of time. All right, so if you struggle with that type still, then just come see me in tutoring because, like I said, I'm literally running out of time. This video is so long. I'm so sorry. If you've held on this long, oh my gosh. You know, we're just going to skip the last one just because I just can't. So anyway, there's the practice exercise. If you want to try it on your own, then there's your answers. The half cell that's the anode is the second half cell, and then the EMF of the cell is 0.105 volts. I'm so sorry I'm phoning it in, but like I said, once announcements come on, then they start releasing the buses, and I have no control over the intercom. All right, so we finished. Again, I'm sorry that I had to run through the Nernst equation so quickly, so if you are still struggling with that, please come see me for tutoring. I'll be glad to slow down in class when I'm not on such a time crunch. And so hopefully these lesson videos have been super helpful for you in getting through AP Chemistry, and hopefully you also realize that that class is not the devil, it's just a hard class that helps get you prepared for college.